Hey everyone, welcome to This Explainer. You know, state-of-the-art AI is absolutely incredible right now. But if you've actually tried putting a fully autonomous system into production, you already know we're hitting a massive wall. Today, we're diving into the source material to explore a huge paradigm shift. We're moving away from just talking to AI to structurally engineering its entire operating environment. Simply put, the scaffolding surrounding the model is now vastly more important than the model itself.
Okay, so let's unpack this shift. An autonomous agent isn't just a model anymore. The equation we're looking at now is simple. Agent equals model plus harness. Think of it this way. The AI model is just the raw cognitive processor. It's kind of like a computer's CPU. But to actually get reliable work done without it hallucinating or, completely breaking things, it needs an operating system. That operating system is the harness. It's the resource orchestrator and the safety boundary that translates all that probabilistic guessing into deterministic, secure execution.
We've got a ton of fascinating ground to cover today. We'll quickly move through the new AI bottleneck, the evolution of AI engineering, the anatomy of an agent harness, the cybernetic governor, some real-world examples, and finally, the trade-offs of true autonomy.
All right, let's jump right into Section 1, the new AI bottleneck and redefining the problem of autonomy.
The crucial takeaway here is that the fundamental bottleneck has completely shifted. Look, it is no longer about whether a large language model can write syntactically correct code or reason its way through a complex prompt. They can absolutely do that. The real challenge now is safe, reliable, and constrained execution in production. The big question is, can the surrounding system govern that reasoning for hours on end without a single failure? Because if an AI goes off the rails in an enterprise codebase, well, that's not just a cute little hallucination. That is a catastrophic deployment disaster. And that, right there, is exactly why we need harness engineering.
Moving on to Section 2, the evolution of AI engineering, from prompting to harnessing.
To really grasp why we need all this structural plumbing, let's take a quick look back. Think back to, say, 2022. We were all heavily focused on prompt engineering, right? We were endlessly tweaking instructions and structuring chain-of-thought steps for just a single isolated model call. Then, around 2025, we shifted to context engineering. We started asking, okay, what exact data should the model see right now? And we used dynamic retrieval to prevent context drift. But now, entering 2026 and beyond, we are firmly in the era of harness engineering. Why the shift? Because prompts and contexts only optimize single turns. They completely fail to govern an autonomous agent that's out there making hundreds of sequential decisions across vast codebases.
Section 3, the anatomy of an agent harness and the ETC-LOVG framework. Let's look under the hood.
So researchers from top universities like Carnegie Mellon, alongside major tech giants, have actually classified this architecture into 7 distinct building blocks. They call it the ETC-LOVG taxonomy. It stands for execution environment, tool interface, context and memory, lifecycle and orchestration, observability, verification, and governance. The bottom line is you can't just let an AI run wild on your host machine. It absolutely needs this deep structural plumbing to act as its boundaries and safety nets.
Now, what's really fascinating here is how these layers naturally team up. On one side, you have the security and sandbox components, like the execution environment and governance. These treat the agent as a distinct, non-human identity, isolating its workspaces using lightweight containers so parallel runs don't contaminate each other. Then, on the other side, we have cognitive support. That's context, memory, and verification. These actively prevent context rot by dynamically injecting structured metadata and enforcing strict programmatic evaluation. We are way past manual vibe checks now. A proper harness demands automated test suites before any output is ever actually committed.
Let's move to Section 4, the cybernetic governor, and balancing constraints with feedback.
This structural plumbing directly shapes software architecture. Renowned software architect Martin Fowler actually frames this harness as a cybernetic governor. It's a brilliant way to think about it. You're basically balancing 2 continuous forces. On the left side, we have feed-forward controls, or guides. These constrain the AI before it even acts. So, instead of giving a vague ticket like fix the login bug, we use in-repository conventions and structured spec sheets to explicitly map out what the AI is allowed to touch. On the right side, we have feedback controls, or sensors. These observe the state after the action. These are your fast, local type checkers and deep CI/CD pipelines that force the agent into a self-correcting loop. All of this relies on ambient affordances, basically a code base that's clean enough for both humans and machines to navigate effortlessly.
All right, Section 5, harnesses in the real world. Let's see how OpenAI, Meta, and Red Hat are actually proving this works.
500%. Just let that number sink in for a second. That is the staggering boost in merged code contributions OpenAI saw within weeks of deploying an open-source orchestration framework called Symphony. Instead of relying on human developers doing manual prompting, Symphony continuously polls the team's project board, spins up an isolated workspace, and just launches an agent. And here's the kicker. To get its code merged, the agent has to submit a verifiable proof-of-work bundle. We're talking green CI passes, full test coverage, even a recorded video walkthrough of the changes. By shifting developers from writing code to simply reviewing code, the productivity gains were absolutely massive.
And it's not just OpenAI. Meta is using their RIA harness for multi-day machine learning pipelines using something called hibernate and wake checkpointing. If a 6-hour task gets interrupted, the harness safely suspends the state and resumes it later, all without losing its reasoning path or wasting a ton of expensive compute tokens. Meanwhile, over at Red Hat, they enforce strict structured workflows. Before an agent can touch a single file, it has to generate a human-reviewed impact map outlining exactly what it plans to change. This is so smart because it prevents the massive token waste and file contamination you've probably experienced when an AI just blindly modifies a codebase.
Section 6. The Autonomy Trade-offs. Let's examine speed, cost, quality, and agency.
Naturally, when you're designing these systems, you've got to ask, if these agents are so incredibly smart, why restrict their tool access at all? I mean, why not just hand them the keys to the database, open up the bash shells, and let them go to town?
Well, here's why. The crucial point is that giving an AI broad access definitely maximizes its capability, but it also geometrically expands your attack surface. This is exactly why the industry has moved to the principle of least agency. You have to strictly limit how much freedom the agent has to act without human approval. Otherwise, you risk catastrophic cascading failures. On top of that, there's a speed-cost-quality trilemma. Deep evaluation loops definitely improve software quality, but they drive up API costs and slow everything down. Plus, and this is wild, shoving too much data into the system triggers a fascinating failure mode called context anxiety. When the context window fills up, the model literally gets anxious. It starts taking erratic shortcuts and skipping verifications just to avoid overflowing. So harnesses have to actively compact memory to preserve the model's cognitive headroom.
Which leads us to our core takeaway for this explainer. The most potent and defensible corporate asset is not the AI model, but the harness built to govern it. Let's face it, state-of-the-art AI models are rapidly becoming commoditized utilities. Almost everyone has access to them now. That means your true competitive moat is the secure, verifiable architecture you build around them to turn that raw potential into scalable, reliable enterprise value. So I'll leave you with this final thought. As we enter the true autonomous era, are you just writing better prompts, or are you building the structural plumbing of the future? Take a hard look at your own workflows and tools. The transition to harness engineering isn't just some optional upgrade. It is the absolute required foundation for the next generation of technological development. Thanks so much for joining me on this explainer, and I hope this gives you a fresh perspective on the real future of AI architecture. Catch you next time.